Hello students, hope you all are doing good. In today's class, we will read a new topic, very interesting, and it's an application to the previous topic. The previous topic what we have read is Kirchhoff's law. So it is one of the example, and this is the topic about Wheatstone Bridge. I'll just give an overview. What is Wheatstone Bridge? Who invented it? And then what's the principle of it? Then we will move on knowing about its construction, working principle, and we'll derive it through our mathematical expressions also. So getting start, like in our world, everything is a question, and the scientists around the world gather together to know answers to various questions the nature has created. The one of the question was in a group of resistance. If there is a resistor which is not having any marking on it, we are not aware how much resistance a particular resistor can provide. How are we going to know about it? So the answer came from here to measure unknown resistance in a circuit Shumail Hunter in the year of 1833 invented Wheatstone Bridge. Okay, now in the year 1833 it was not a very popular thing, but in the year of 1843, after just 10 years later, Sir Charles Wheatstone popularized it. Okay, now next to it was this Wheatstone Bridge is too known as resistance bridge. Why? Because it is used to measure the unknown resistance. Okay. Calculates the unknown resistance by balancing the two legs of bridge circuit where one leg includes component of unknown resistance. So it have this bridge, Wheatstone Bridge, Wheatstone Bridge. It have four legs. Four legs. In these four legs, two we have connected with known resistance. One have the variable resistance and the last one have the unknown resistance which we need to find out. Okay, now I have told this is based on the principle of Kirchhoff's law, and then there is another principle which is the null deflection. Principle, that is null deflection. Now when we will go ahead in this topic, I will explain you what null deflection is and how our Wheatstone bridge is following this null deflection principle. Now, Wheatstone bridge is an application of Kirchhoff's rule. Bridge has four resistors R1, R2, R3 and R4. Across one pair of diagonally opposite points, a source is connected. Just I'm making a diagram over here because the diagram is on the next page. The Wheatstone bridge looks something like this. In these two pairs, we will have a voltage source connected, and along this we will have one galvanometer connected. This will be R1, R2, R3, R4. Okay, these will be the resistors. This is called battery arm. So which is the battery arm? This is the battery arm. Battery arm. Between the two vertices, a galvanometer G device to detect current is connected. This, see, and this arm is called galvanometer arm. Next to it, for simplicity, we assume that the cell has no internal resistance, because if we are adding this component in our derivation also, we have to include this, and the problem will become bit complex. So to remove the complexity, we are not using any internal resistance. We are saying that our cell have no internal resistance. In general, there will be currents flowing across all the resistors as well as a current Ig from G. Okay, the current flowing through galvanometer is termed as Ig, current through galvanometer. The balanced bridge is one where the resistors are such that the current flowing through the galvanometer is zero. No current flows through G. No current in galvanometer. Okay, in this case, the Kirchhoff's junction rule applied to the junction D and B immediately gives us relation that I1 equals to I3 and I2 equals to I4. Now, where is I1 and I2? In the resistor 1 I1, in resistor 2 I2, in resistor 3 I3, here I4. I'll redraw it to make you understand it more properly what the last statement is trying to convey. Okay, I have derived in these notes relation in one way, and in a rough page I will derive the same equation in another way, so that you will have two ways how you can derive an equation for the Wheatstone bridge. Okay, so this is one resistor, this is another, the third one and the fourth one. Okay, if this current in this current becomes zero, this will be like there doesn't exist any such branch. Okay, no galvanometer arm exists. If Ig equals to 0, we can assume no galvanometer arm exists. Okay, now when we are assuming these two will have the same current, the current flowing here will flow from here, from R1 and R2, sorry, R3, the current flowing is same. Similarly, the current flowing through R2 and R4 will also be the same and equal. I1 equals to I3 and I2 equals to I4, because there is no junction at their meeting point. These resistors R1 and R3 are connected in series. Similarly, R4 and R2 are connected in series. So, any resistor connected in series have the same current flowing through them. So, this is one of the condition. Now applying Kirchhoff's loop rule to the closed loop ADBA. A from here, D, B, A. Okay, in this loop, I'll highlight it. First of all, we are trying to apply Kirchhoff's rule here. Then we will apply Kirchhoff's rule over this. Okay. When we are applying from the first loop, we are getting I1 R1 plus 0 because in this there is no current flowing. Through galvanometer, no current flows. See, Ig equals to 0 plus I2 R2, which will give us value equals to 0. So upon solving this equation, we will get I1 R1 equals to I2 R2. I brought this equation to RHS. Okay, so this is one of the relation. Second relation, the second loop gives us I2 R4 plus 0 minus I1 R3 because here I1 equals to I3 and I2 equals to I4. Now I will solve this equation. We will get I2 I4 equals to I1 I3. Now from equation 1, we will find the ratio of I1 is to I2, that is I1 upon I2. This will be, when this is going here, this will go in the denominator of R2. It will be R2 upon R1. Similarly, I will find the ratio of here. It will be I1 upon I2. This I2 will go here. So I3 will come here. It will be I4 upon, this is R4 upon R3. R4 upon R3. Okay. Now this equation and this equation, we got two equations which are having the value for I1 and I2. Equation number 3 and equation number 4. Now I will equate equation number 3 and 4. What I will get is R2 upon R1 equals to R4 upon R3. That is ratio of resistance R2 and R1 is equal to the ratio of resistance R4 to R3. Okay. Now we will obtain this relation R2 upon R1 equals to R4 upon R3. That is our finalized fifth equation. This equation 5 relating to the four resistors is called balanced condition for the galvanometer to give zero or null deflection. Now when there comes a null deflection, I will explain when the resistors in four arms show equal resistance or R2 upon R1 equals to R4 upon R3, which is a balanced state. Balanced state, the galvanometer will show no deflection. When a galvanometer is showing no deflection, that implies that in the galvanometer there is no flow of current. No flow of current through the galvanometer. Okay, that is zero or null deflection. Okay. Now the Wheatstone Bridge and its balance condition provides practical method for determination of unknown resistance. That is one of the very important application. Important application. Let us suppose we have an unknown resistance which we insert in the fourth arm R4 and is not known. Keeping the known resistance R1 and R2 in the first and second arm, the bridge we go on varying R3 till the galvanometer shows the null deflection. The bridge then is balanced And from the balanced condition, the value of unknown resistance R4 is given by the equation R4 equals to R3 into R1 upon R2. A practical device using this principle is meter bridge. I will explain this here. The fourth point, just see, we are having the two resistance R1 and R2 which are known. Let's assume R1 is 4 ohm and R2 is something like 16 ohms. Now R3 is a variable resistance, and R4 is unknown to us. But we know that R2 upon R1 equals to R4 upon R3. Now we know this, This is variable and we doesn't know this. Now I will start like changing the variable resistors value. I will start changing the variable resistance value, and I will keep on changing this value until I am getting Ig equals to 0, and at this particular point galvanometer attached will show no deflection. Galvanometer will show no deflection. So at this point I will be able to find the value of R3. Once I got the value of R3, let's assume it is 9 ohm. Now I can find out the value of R4 using this particular equation. Now if I substitute these particular values I have assumed over here, then it will be R4 equals to 9 into R1 is 4 upon 16. This will give us 4 upon 4 and R4 is 9 upon 4 ohms. Okay, like this we have to solve. Now I'll summarize it and I will give you one more, a simple derivation for your understanding. Okay, we have seen how the Wheatstone Bridge was invented. So what are the components of Wheatstone Bridge and what is the construction? Component and construction. Okay, component of a Wheatstone Bridge are two known resistors, one variable resistor, and one is our unknown resistance whose value we need to find out. Now for the construction, we will see there are four arms like this, and here is a galvanometer attached, and here is a source attached. I will take here one resistance, second resistance, third resistance and the fourth resistance. Okay, and I will give name it as PQRS. Here current flowing I1, here current flowing I3, here current flowing I2 and here current flowing I4. From here the current is I, going I, coming I. And in this direction the current flowing is Ig. Hope you have got the diagram. In this case we can say that P, R are known, Q is variable and S is the unknown resistor. Now principle for this is it's based on null deflection, that is ratio of their resistance is equal and no current flows through the circuit. Okay, so now when we are saying that no current flows, this one particular arm gets lost, like it's not visualized. Now the circuit remains like this. Here we will see that P and Q are in series having same current flow, having same current, current, and next to it is R and S. The same condition goes with them, in series having same current. Now from here the current I1 is flowing in P, which is equals to the current I2 flowing through the R. Okay, similarly I1 equals to I3. Like if I say these two arms are equal, this will give us current into 1 into P equals to current into 2 into R. This is coming from the Kirchhoff's loop rule. Okay, and now I1 equals to I3, which is equals to EMF. Here whatever EMF is there, EMF divided by P plus Q, and this is coming from Ohm's law. How come? I'll make another equivalent diagram of this. This diagram can be visualized as like this. Okay, here and here the current is different. From this I1 is flowing, this I2 is flowing. It is PQ, this is R and S. Okay, and this is our EMF E. From the parallel and series combination, we have read that the voltage in these two parallel combination will be same, but the current will change. Voltage in parallel connections is constant, but current divides. Okay, so that is the rule. The current I1 and I3 is equal, so this will be equals to the voltage across P and Q divided by their equivalent resistance, that is P plus Q. Now if we want to find the equivalent resistance of this, it will be equals to P plus Q because they are in series. Similarly for this it will be R plus S. Similarly I will say that I2 equals to I4, which is equals to E upon R plus S. Okay, E equals to R upon S. Now I have got this one equation and this one equation where I know the value of I1 and I2. I will substitute the value of I1 and I2 from these two equations in this first equation, which I have got through Kirchhoff's loop rule. Okay, I1P equals to I2R. I know I1 equals to E upon P plus Q and I2 equals to E upon R plus S. Substituting this value, E upon P plus Q into P equals to E upon R plus S into R. This E and E is common in both. Now this will give us P into R plus S equals to R into P plus Q. I will solve it. This will give us PR plus PS. Here also PR plus QR. Okay. This and this are same, will get cancelled out. So PS equals to QR. From here I will get P upon R equals to Q upon S. So this is again one of the solution. I will make the diagram once again for your understanding. So This was 1, 2, 3, 4, and this was P, Q, R, S. So P upon R equals to Q upon S. Okay. In this, somehow we have to show the null deflection in our galvanometer, which we have shown. If we say that our R is the unknown, just a minute, I can write this particular equation in another form that is more convenient, that is P upon Q equals to R upon S, this one and this one. Okay, this is more convenient, so derive it in this format. Over here we will see that if I say R equals to unknown resistance, unknown resistor, then R equals to S into P upon Q. From this equation we can find this R, unknown resistance. Now it's high time for us to know the application of the Wheatstone bridge. Just I'll write the keywords here, you keep on writing it. Precise measurement for the low resistance gives us precise measurement for low resistance. This happens because we are using a galvanometer which can show deflection in milli and micro amperes also. So it can show the changes even there is a slight change in the current. I'll not say the slight, but I'll say extremely slight changes there, it will show. Now, Wheatstone bridge, an operational amplifier used to measure physical parameters. What are these physical parameters? Such as temperature, light, and strain. Okay, Wheatstone bridge plus our operational amplifier. Operational amplifier will you will be reading it in your 14th chapter, that is semiconductors. Okay, at that time we will discuss a lot about it. When these two are combined, they are used to measure the physical quantities like temperature, light, and strain. Now the third one, quantities such as impedance, inductance, and capacitance can be measured using variation in the Wheatstone bridge. Quantities like impedance, denoted by Z. We will read this when we will be reading electromotive forces, that is just after 2 chapters. Okay, then inductance, again this will be read in the in this series. If you are going in the next 2 chapters, we will be reading inductance denoted by L, and capacitance. We have read about it previously. These can be measured by Wheatstone bridge, but we have to do the nominal changes. Okay, measurements can be done using variation in Wheatstone bridge. Okay, now we'll move on the limitations. When we are having applications which are very much helpful to us, what are all are the limitations given by this particular instrument? I just think that this instrument is very good, very helpful, and we can overcome such limitations very easily. So we are not going to use it less. We'll be using meter bridges more, Wheatstone bridges more. But we need to discuss on the limitations. So when we are becoming engineers, we can overcome these. Okay. For low resistance measurement, the resistance of the leads and contacts became significant and introduce an error. Okay. In case of low resistance measurement, what is happening? The resistance of leads and contacts became significant. The connections have more like when we are a resistor is having low resistance, but the wires connecting it, the circuit connecting it, having some of its self resistance which dominates such things, so it became significant. Resistance of non measuring things became significant, causing error in the measurement. Okay. Now next to it is for high resistance measurement that we have talked about the law. Let's talk about the high resistance measurement. Measurement presented by the bridge is so large that the galvanometer is insensitive to balance. So large that galvanometer becomes insensitive to it. Why is it happening so? Because galvanometer is a device which is used to measure very small amount of charge. When a resistance is of high resistance, what happens is that the galvanometer is unable to show that high current deviations. So it becomes insensitive. Now we'll see the third and the last. Resistance changes due to current heating effect. Our wires, they get heated up when we are using our meter bridge again and again. So the resistance is something which is dependent upon the temperature. We have seen this equation RT equals to R naught into 1 plus alpha T2 minus T1. This particular equation shows for a particular material how this material will change its resistance when temperature is changed. So when this heating resistance changes, when current heating effect, current heating effect through the resistance excessive current may even cause a permanent change in the value of resistance. Okay, and if there is excessive of the current passed, excessive current may permanently change the resistor value. Okay, and this can also happen. So we cannot excessively use the meter bridge continuously. Like in case if we see that there is an error and we want to redo everything, we have to give some time for all these our electrical equipments to settle down so that we can perform it on a better scale. And we have to use wires which are not getting heated up for the after we are using excessively. And if we are using such things, we are making it more costlier. So we have to design it in such a way that we can use it over a longer period with less current heating effect, and with a galvanometer which can even show us the deflections in current when high resistance measurements are there. And in case of low resistance measurement, our wires, our circuit should not have higher resistance value, or we must use something which is having equivalent to zero resistance so that there is no such limitations can arise. Hope you understood this topic well. In case of any doubt, you can just simply ask the questions in the comment section. I'll just try to answer all these, and try to correlate this topic with the previous topic you have read so far and the application of it. I have took this one extra page by telling you the applications and limitations beyond the NCERTs because of the reason that if you know why we are using this meter bridge, you will be able to remember its formula more concisely and more like in a precise way. So try to correlate this, understand it, and read it properly. Have a good day. We'll meet in the next class with a summary of this chapter. This chapter is over. This is the last section of the chapter number 3. In the next class, we will summarize the whole chapter number 3, that is electric current. And then we will see some points which needs to be pondered, which needs to be thought about. We'll meet in the next class with a summary of the chapter. Till the time, keep reading, keep growing, and yeah, continue practicing. Practice all the example problems, practice all the NCERT problems so that you understand these topics more well. If you are solving a question, you will be able to remember these topics more easily rather than just mugging up these topics. Okay, bye bye, have a good day.